Okay, so moving on to the third configuration, which is RAID level 4 or RAID-4. It's also called block interleaved parity, where instead of using direct redundancy, direct data duplication, or replication technique, it uses algebra kind of parity calculation technique to support storage capacity efficient redundancy. Okay. So this is so-called capacity efficient redundancy. It does support some level of redundancy, but instead of using direct, data duplication or data replication, it uses computation, a trade-off computation overhead for storage capacity. Okay. So before getting down to the detail of how RAID-4 works, let's take a look at the motivation that really motivates the design of this third configuration, which is RAID-4. So here in this slide, we're looking at this two-dimensional scatter plot, and the x dimension or the horizontal dimension is capacity. Okay, how much data, how much unique data that you could store, and the y dimension is reliability. Okay. Reliability is how many disks that you could tolerate, how many disk failures you could tolerate, how many failures, okay? And here, the higher the better. Again, capacity, the higher the better. Okay, so far we've covered two basic configurations, RAID-0 and RAID-1. Okay, so where exactly these two configurations lie in this two-dimensional space? As you can see in this slide, RAID-0 lies on the right-hand side and RAID-1 lies on the left upper corner. Okay, why is that? It's because RAID-0, it serves as it sacrifices reliability, it provides zero reliability, but it does provide the best capacity efficiency because it doesn't use redundancy at all. So RAID-0 represents one stream stream at this spectrum, this two-dimensional spectrum. Here, we're not considering performance at the third dimension. We don't consider performance so far. And on the other hand, RAID-1, it does support better reliability because it could be used to sacrifice at most, I mean, in theory, best case, 2 disk failures, but in most cases, 1 disk failure. Comprehensively combine these two together, it could sacrifice, it could tolerate 1 disk failure, but that is still better reliability. But this comes with sacrificed capacity efficiency, okay? In terms of capacity, it is lower. In terms of capacity, RAID-0 is higher. So, but we want to combine the best of both worlds. We want both higher capacity efficiency and at the same time, we want a higher reliability. So basically, we want a new kind of configuration to be able to effectively combine the best of both RAID-0 and RAID-1. It should be somewhere over here, right? So this is the best of both. So that is why we have RAID-4, okay? RAID-4 is over here. It combines both RAID-0 and RAID-1 by using parity-based redundancy support. Let's see how exactly it uses parity, okay? So strategy-wise, again, as I mentioned, it does use parity disk. Instead of using 4 disks, it introduced 1 more disk, which is the 5th disk, which is solely used as storing data parity. But what exactly parity? What exactly is parity? So let's say in algebra, if an equation has n variables, and this is a linear, right? and there are n-1 are known ahead of time, you can also solve for the only left, which is unknown, right? So for all the binary operations plus addition, subtraction, or even exclusive OR, right? XOR, right? These kind of binary operations are commonly used for supporting this parity calculation. Okay. And basically, to put it into the context of a RAID configuration, you treat the sectors or the disk blocks across different disks within the stripe as some sort of an equation. And then the objective, the mission, the task is to, whenever there's a disk failure, you apply this equation to calculate, to solve this unknown. Okay, so this is a simple strategy. So again, the failed disk is like an unknown in that particular equation. Just apply the equation. Simple. So let's take a look at a specific example. Instead of having 4 disks, we introduce one more disk, which is called parity disk. Okay, so this disk number 4 is used to store parity. And over here, we have P0, P1, P2, and P3. These are the parity that are calculated by using the regular data. So here, all these data are called regular data. And this is the parity chunk. Okay, regular data chunks. Okay. All right, so let's say we're looking at the first stripe, and the 5th chunk within the stripe is the parity chunk. In this case, let's assume we use addition. So the regular data chunks are 4, 3, 0, and 2. So let's assume we use addition. Okay? To add these up together, these 4 elements together gives you 9, right? So the parity chunk is 9. Okay? So let's say at a single point of time, disk 0 failed. Okay? So the data chunk stored within disk 0 gets lost. So we could just simply apply this equation. We do 9 minus 2 minus 0 minus 3. So these 3 are essentially these available existing data chunks. So that calculates 4. So we use this 4 to recover the lost data. So 4 it should be. Okay? So this is how exactly you use this binary operation, the parity calculation, to basically add a little bit more computation overhead. For better capacity efficiency. Okay? This is a trade-off that we're looking at under RAID-4. Okay? So that just provides a really simple example of using addition or add operations. In practice, the most commonly used parity function is called exclusive OR, or XOR, whatever you like to call. So how to calculate XOR is by following these rules, right? So if the total number of ones in a stripe is an even number, then the result of this exclusive OR operation is 0. So the parity value for that particular bit or digit is 0. On the other hand, if the total number of ones within the stripe is an odd number instead of an even number, so as a result, the parity bit is 1. Okay? If you apply this policy, in this case, this top stripe, it has a total number of 2 ones, which is an even number. So the result of exclusive OR is 0. If you take a look at the second stripe, the total number of ones is an odd number, right? So as a result, we have the XOR result is 1, okay? So in this case, let's put it into the context of a RAID-4 configuration. So each block in this case can represent 2-bit, right? 2-digit, okay? So this stripe, you calculate the stripe by using exclusive OR, right? 0, 0, 0, 1, 1, 0, 1, 1, 1, 0 gives 1, 1, okay? You do the same XOR on the second stripe, okay? Again, let's say block 0 or disk 0 gets down. So we want to calculate that. You could apply exclusive OR to the rest of the 3 data blocks together with 1 parity chunk, parity block, okay? You just do exclusive OR on block 1, block 2, block 3, and the parity block. That gives you, so the high bit, we have a total number of 4 ones. So that gives you 0. So the high bit is 0. If you take a look at low bit, we have total number of 2 ones. So that gives you zeros as well. So the low bits, high bits, both 0. So we just get that recovered. As a result, the block number 0 should contain data 0, 0. So this one gets recovered with 0, 0. Okay? So this gives an example of how to use XOR to recover the data. And if the parity data gets failed, what if the parity data gets failed? Well, basically apply the same equation, okay? If this thing gets failed, you do XOR on top of the 4 available data chunks, the 0, 0, 1, 0, 1, 1, 1, 0 gives you the parity chunk, which is 11, which is 1, 1, right? Okay, you just apply the same theory. So let's get to the theoretical analysis part. In terms of RAID-4, so the capacity, assume n is a total number of disks that get involved in this configuration. Because we introduced this extra disk as the parity disk, so the total amount of effective capacity that could be used, effective capacity that could be used to store data chunks or data blocks is n-1, right? Excluding the parity disk times C, assuming C, letter C represents per disk capacity. Okay, so get to the second point, which is the reliability metric. How many disks can fail? In this case, we have n-1 for data, and we have 1 for parity, right? In total of n disks. It could at most tolerate 1 disk failure, because recall that we use that linear equation, which is a process of computation to help recover that single disk that gets lost. It could only be tolerating 1, at most 1. If you have 2, the parity doesn't work, okay? So we have to introduce other more sophisticated parity calculation. That is slightly out of the scope of today's lecture. That is more, kind of like erasure coding. Coding theory, we have like data chunk, and we have parity chunk. If P is equal to 2, data is equal to 4, it could be used to tolerate at most 2 failures. Something like that, but this is slightly out of the scope. Okay? So that you know. So getting to the performance throughput. For the first three, sequential read, sequential write, and random read, is n minus 1 times S or R, right? Because we're talking about like, so for sequential ones, it just sequential linearly scan through a large chunk of data. And here we're not considering, for both read and write, we're not, if you're talking about read, let's first talk about read. For read, it's easy to understand. It's n minus 1 times S, right? Because you don't want to include the parity data, the parity chunk. Parity doesn't contribute to the actual data. It can only be used for recovering the failed data. But for a sequential write, so Y is also n minus 1 times S. It's because over here, we apply one kind of write, sequential write optimization. So in this case, let's say we have 5 disks, D1, D2, D3, D4, and then parity disk, okay? So we store 1, 2, 3, 4, P0, and the 5, 6, 7, 8, P1, something like that. So this optimization, what this optimization does is it could apply the sequential write single at one time. This sequential write at one time as well. And then you calculate the updated checksum, you updated parity data afterwards. So that is kind of overshadowed or, amortized. The overhead of calculation is amortized. So that is why it's n minus 1 times S. So there's a more detailed description about reasoning about this performance analysis. So definitely, so in the textbook, definitely read the textbook, okay? It's really important to read the textbook for this chapter, the RAID, the working mechanism and the performance reliability analysis part, okay, to get a deeper understanding. For random read, it's easy to understand. It's n minus 1 times R, okay? Because you have only n minus 1, these many disks to contribute to the read performance. For random write, it's a little bit trickier, which is R divided by 2. Why is that? So here, let's talk, if you take a look at this example, random write. So it could happen to this one, to this one, to this one, to this one. We're talking about random write that are concurrent issued to all of these 4 disks that are used to store data, right? But each random write, so each random write, it gets effectively translated into each logical write, I would call it logical, gets translated into 2 physical write. Why is that? Because you need to first update this guy, and at the same time, you need to update this guy as well, right? So it gets translated into 2 physical writes. So that is why you have a factor of 2 divided by 2. So this is a random write. And in terms of random I/O latency, this is the read latency, which is D, because you just simply read one data chunk or data block out from disk. For write operation, it is 2 times D. Why is that? Again, because the random write performance is the single write operation, single write, logical write gets translated into 2 physical writes, okay? 2 physical write, 2. So this is where this 2 comes from, okay? So this is that completes RAID-4. So in this slide, it uses example to further illustrate the analysis process of the random write to basically reason about why a random write is R divided by 2. Okay? All right, so in this example, let's say we're talking about random writes that hit on logical block 4 and logical block number 13, these two, okay? But these two gets translated because in order to update this like data block, you have to update the parity as well, respectively. And logical block 4 has its corresponding parity block stored in disk, the fifth disk, which is disk number 4, okay, which is P1. And if you want to concurrently update another logical block, which is not logical block 13 stored under disk 1, its associated parity block is stored in disk 5 and disk 4 as well, which is parity 3, okay? So this boils down to this so-called small RAID problem, okay? So for small RAID, because all the small RAIDs gets effectively serialized at this single point of bottleneck, which is the parity disk, okay? So gets serialized within the parity disk. That further gets translated into two physical RAID, right? So the first physical operations is you need to read the parity chunk out. And the second operation, physical operation, is you write the updated parity chunk into the disk from the memory. So each logical I/O gets translated into two physical I/Os, one read and one write. So that is why for the random write performance, it's really bad in terms of for RAID number 4, which is R divided by 2. So this is how this R divided by 2 results comes from. How to calculate R divided by 2, okay?